enjoying the food here. So now this idea is trying to connect neutrino with diameter. Okay, so the motivation, the brilliant motivation is if you look at the existing models in the market. So there are many models trying to connect diameter with neutrinos, but it's hard to make predictions. How heavy the diameter is, no definite answers. Just by, okay, the input is the neutrino mass. Then given neutrino mass, can you predict dark matter mass? And the answer is, to my best knowledge, is no. So based on these kind of motivations, so I try to propose a very, very simple ideas, trying to connect the neutrino mass with diamond mass. Okay? So first of all, I'll briefly mention discussion. I'll briefly mention evidence of diameter and neutrino field, the evidence of diameter and neutrino mass. Okay, then I'll work on the effective Lagrangians, try to connect diameter mass with neutrino mass, and then I'll provide the UV combi model. Okay, and I will conclude. So then, since this one is a very simple ideas, so it will be short. Okay. So first of all, let's look at the evidence of neutrino oscillations. Okay? And now there are two main evidence. One is from atomless neutrinos. Okay, the other one is solar neutrinos. Okay. So this one is from the superconductor Conta. It's first observed back in 1998. Okay, so this one is the zenith angle. This one is the neutrino flux. The muon neutrino flux. This is the zenith angle. Okay, the zenith angle 1 means is pointing toward the zenith. It's the neutrino coming from above. This one -1 is the neutrino coming below. So okay, so we know the cosmic ray bombard our atmospheres, which produce a lot of neutrinos. Okay, so which will be picked up by the large water tank by the Cherenkov. Okay, so and if you don't consider neutrino oscillations, then the red line is the theory predictions, since we can estimate how many neutrinos will be produced from the cosmic ray. Okay, and actually what we observed is the green line here. Okay, the neutrino from above, since the baseline, the travel distance is short, so neutrino they don't oscillate. It's too short for them to oscillate. But for neutrino coming from below, since they can penetrate the Earth, so they will oscillate. So actually, we kind of see this kind of deficit. Okay, so that's the evidence. Actually, the neutrinos they do oscillate. Okay, the other one is from the solar neutrinos. Since the solar they have a lot of nuclear reactions, so the electron neutron will be produced. Okay, so we have theoretical predictions on how many electron neutrons we can observe from on Earth. Okay, so that's the theory predictions, which is based on different experiments. So they're like chloride, water tank, and heavy water, etc. Okay, so this one is theory predictions, but what we observe actually is is less than the expected one. So which means actually neutrino flavors is not the mass eigen state. They will oscillate and into different flavors. And to give you the rough ideas, this one is the neutrino oscillation probabilities from neutrino alpha into the beta flavors. Okay, which of course proportion the missing angle theta, and also delta n squared L and the E. The delta n squared is the mass square difference between neutrinos. Okay, so if neutrinos are warm masses, which means all the mass are 0, so the delta n squared will be 0. So there will be the no oscillations here. Okay, so non-zero oscillation probability implies non-zero theta, non-zero missing angles, and also the non-zero delta n squared as well. Okay. One thing I want to emphasize, actually, from neutrino oscillation alone, actually you can only determine the mass square difference, but not the absolute net mass. Okay. And I'll skip this one since it's been mentioned many times. Okay. So here we propose a very simple one. How? So if you just look at these effective couplings, right? Two diameter, KIAS diameter, and nu is neutrino. Okay. So throughout this presentation, I work on the wire spin notations. So the one without dagger means left-hand chirotic. The one with dagger means right-hand chirotic. But basically, it's the same as full component spinners. But it will be clear to use in my opinion, wire spinner notation in this case. Okay. So if I write down this one here, so that's the only coupling. If that's assumed, that's the only coupling connecting diameter with neutrinos, chi nu nu. And of course, we impose Z2 symmetry to make that diameter stable. Okay, so that's the only one. So you can, first thing you will notice, actually this one breaks SU to left, right? Since neutrino is embedded into the SU2 doublet. Okay, but as we shall see below, the actual scale here is actually lower than electronic scales, so it's okay as long as you conserve the U1 charge, then it's fine. Since at that scales, the electronic symmetry has been broken already. Okay, so that's the reason why we can justify the explicit SU2 breakings in this kind of static company. Okay? Now, how do we get this one here? So we have to kind of introduce kind of scalars phi, which connect the chi, the diameter, with so-called one-bar operators, right? So usually the one-bar operator is dimensional phi operators, which give a mass to neutrino. Okay, so with introduction on phi here, and we can just integrate out phi, and then after integrating out phi, one can reach this one here. Okay, so now here comes the important things. If you stare at this Lagrangian here, if I assign my charge the lepton number set, if I assign my lepton numbers in this way, the chi I assign -1, right? And the phi I assign 2 here. Okay, so this one -1, -1, 2 is 0. So this one conserves lepton number. Okay, let's look at this one. This one is 1, 1. Sorry, this there 1, 1. This one is complex conjugate, so it's -2. So the whole thing actually conserves the lepton number, which means actually in this context you cannot just write down a one-bar operator since it breaks lepton numbers. Okay, so then that's the key point to connect diameter mass with neutrino is in terms of the effective languages. So only the lepton number violation comes from diameter mass. Okay, so which can come from some hidden sector, as I will mention below. So right, this one is -1, -1. Here is -1 lepton number, -1. This one is 0. So the whole thing carries the -2 unit of the lepton numbers. Of course, it violates one. Right? So and the diameter mass could result from some hidden sectors. So the hidden sector doesn't couple to a small sector, but directly, but only through the diameter. So that's the key point to connect diameter mass with neutrino one. Okay. So as I mentioned here, so if you switch off the diameter mass, the neutrino mass is 0 because this term actually violates lepton number by 2. So it has to be induced from diameter mass. So that's the first observation. Okay. So now let's look at how this effective coupling can generate the mass to neutrinos. This one here. Okay. From this one, it's simple, right? Since my diameter is Majorana, it gets a Majorana mass, right? So once you connect, kind of close loop, this one is a loop induced one. So you generate the mass to neutrinos. So it's in this form. But there are 2 contributions. One has different chiralities. Okay. So in this case, we use the dimensional regularization schemes with the minimal subtractions, just technical details. But the key point is actually if this one can be justified, since one might ask, since this one is the effective field theory, how can you use dimensional regularization, which is based on the UV complete models? My argument is, if your UV complete theories has exactly the same the structures, then you can just use DR. Okay, so which I will justify later. The key point is if the UV one has exactly the same diameter loop here. Okay.
Sorry.
Yes.
The scale 5 divided lab.
Sorry, say that again?
Scale 5. Yeah, talking about 5 chi.
You mean this 5 here?
Yeah, 5. Where is divided lab? Vacuum.
No, it doesn't get. It has been integrated out. In the low energy theory, I only have 2 species. One is diameter, one is neutrino.
Okay.
So, yeah, after integrating out the 5, one can reach this one.
Yeah,
So, yes.
I mean, in this case, actually, after the document will induce linear difference to 5 after the loop chi.
Exactly.
Yeah.
Exactly.
So I mean, probably 5 will get a lab.
Yes. You're
So
right.
in
Yes.
this case, the second operator will give mass
Exactly. So actually, they are equivalent. It depends how you want to see it. Yeah, you are right. You are definitely right. So you can see in two ways. The first, you just close loop. You just close loop. You compute this one. Second, you look at this one actually induce the linear turn on phi, and the phi gets a back.
The same.
They are equivalent.
Same result.
Yeah, you yes, they are the same. Why they are equivalent? You cannot double count. So they resolve to the same thing. You are definitely right. As we will see in the UV complete one, that's the case. Yeah, thanks for pointing that out. Okay. Now let's look at the diameter annihilations, right? We have four fermion interactions, right? So there are two. There are two contributions, right, from different charities. Okay, so you can compute the cross section from these simple diagrams. Okay, but one thing I want to emphasize is the interference terms between these two actually is zero, because it's involved character flipped, so it's proportional to mass on both initial state and final state. But because the final state are neutrinos and they are nearly mass states, so interference is zero. So in other words, actually the energy cross section is S wave dominant. It's not P wave. It's S wave. So if I were to write down in terms of the four component spin notations, I use phi chi c bar gamma phi chi has gamma phi inside, so that's S wave, not P wave. Okay. Now that's the like high school maths, right? So we have two unknowns from these effective operators. One is n chi, the other is the lambda, right? We have two conditions. What are the two conditions? First, visual mass, of course. The second one is the break abundance, which actually depends on annihilation cross section, right? So given the two conditions, we can uniquely determine n chi and lambda. So that's so simple. Starting from these effective operators, the two unknowns can be completely fixed once we supply the diameter abundance and neutrino mass. Okay, so to give, since this one is like it's like toy model, so we just explore the one flavor case, okay, which we choose to be heaviest active neutrinos with a mass around like 5 times 10 to minus 5 to 0.2 EVs. So actually you can get this one. As I should argue before, from neutrino oscillation alone, we only know the delta n squared. But actually from Planck, they impose constraint on the sum of the neutrino masses. So it's less than 0.6 EV, roughly, from the Planck data. So which can constrain the heaviest one to be this range. Okay? So to give you an idea, so we make a plot. This one is n chi, the one is lambda here. Okay? And this line, the blue line, corresponds to the neutrino mass with 0.2 EV. The one is 5 times 10 to minus 2. Okay? So the range is around this one. And this one corresponds to a correct gradient abundance. It's 0.12 from Planck. So this region here is corresponding to lambda, roughly 1 GeV, and n chi is 0.4 MeV, right? So that's the key point for this paper. So actually we can somehow predict the neutrino mass, the diameter mass from neutrino. Okay, now here I provide a kind of toy model, it's UV complete one. So first of all, I introduced the capital phi chi, which is in the hidden sector, okay, which if you carries the delta number as well, right? Once it picks out VAF, and you give the minor mass to diameter, so it's on this side. And keep in mind, the phi chi here is only in the hidden sector, and it couples to the stem-mount sector only through the diameter loop. So first of all, I want to point out actually is exactly the same loop diagrams as before, okay, but we just UV complete, okay? Then phi is the phi before. I introduced to connect neutrino and diameter, okay? But to UV complete the one per operator, LH, I include the Dirac heavy neutrino, okay? Why Dirac? Since we know from type 1 CISO, we can introduce minor neutrinos, right? Heavy minor neutrinos, which can give a mass to neutrino. But once you do so, then there's no connection between diameter and neutrino, since you already have the lepton number validating source from heavy neutrino. So you have to introduce the Dirac neutrino here. Okay, so to summarize, only the lepton number violating source comes from the UV1, and it gets passed down to a neutrino only from diameter. So that's the key point to connect neutrino mass with the diameter mass.
So does the phi get bad?
Oh, sorry. Oh, give me a few seconds, I'll mention. Yes. So once the phi chi gets it breaks lepton numbers, so give a mass to neutrinos, and the lepton number is passed down to neutrino via diameter. Okay. And the scale, actually, if you look at its scale here, okay, in the effective zero, actually can be obtained. You can just read the lambda by integrate out the phi, c, and n, right? So you can read out and also include coefficients. So lambda is very simple. Lambda is like this form here, okay? And now, as I mentioned before, the capital lambda is around 1, okay? If we just assume, all the coupling constants is 1, right? The C, all C is 1. Then the phi here, actually, if you move the YB and NN to the left-hand side, this one, actually YB divided by NN is the neutrino missing angles, right? Which is constrained from electric precision test, is less than 0.1. So, which means actually N phi is constrained to be 0.1 GeV, but it has to be larger than 1 NeV. Why? Because my diameter is of like roughly 1 NeV. And the reason why I can remember before, I introduced phi to Fermi to reach the 4 fermion interactions. So actually the capital phi here has to be heavier than my diameter. Otherwise, this effective approach will break down. So, but from this one here, actually you can infer my heavy the Dirac neutrinos is around 1 TeV to 1 TeV. It's just simple math, you just plug in. If this one is 1 NeV, 2.1 GeV, then you can infer the NN is 1 TeV to 1 TeV to 100 TeV. Okay. Now, to answer your questions, alternatively, without integrating out the heavy particles, one can look at the UV complete one. So that is to include all the heavy neutrinos to look at the heavy neutrino mass. Okay. So the diameter mass actually induced mixing between these two guys, right? And once this one gets VAV, the phi chi gets VAV, it will trigger a small VAV 35. Okay? But the capital phi talk to a KC, right? So actually give a small mass to a KC. That's the neutrino mass. Sorry, minor mass, which breaks the number. Okay? So if you were to write down the complete mass matrix in the base of neutrino, the heavy Dirac neutrinos, right? Dirac neutrino means 2 pairs of monomer species. It's N and C. So this one is induced by diameter loop. Okay? So if you can try to diagonalize this one, okay, then you can get neutrino mass. And then you compare neutrino mass just with another one just by looking at this one and contrast these two here. And then you can infer lambda. The lambda is just like this one here. So there are 2 ways to see it. First, you can integrate out all heavy particles. Second, you can look at the complete, the mass matrix, then you can infer this one. Okay? And yeah, to answer your questions, yes. So this guy actually has small VAV coming from this one, and it's mediated by the diameter loop. Okay, so that's the key point to connect diameter mass with neutrino mass. And in fact, if you are familiar with the inverse Caesar, this is just inverse Caesar. It's a realization inverse Caesar.
So you mean the inverse Caesar, the Madrona mass is generated by loop?
In this case, yes. But the original paper, they have like string theory motivation, which I don't quite understand, but just like this term. Yeah. Without this term, the lattice one is 0, right? If this one is 0, then you take determinant is 0, which means the lattice one actually is 0. Okay. So, but there are two important ingredients for this UV complete one. Actually, first, as I tried to mention, the lepton number violation actually comes from hidden sectors. But these hidden sectors, they don't talk to the thermal sectors, only through the diameter. That's a connection, okay? And the heavy particles, they are being integrated out. Actually, they do not enter the diameter loops. Okay, that's the very distinguished features of this model from existing models. The famous one is like probably you know the like the scotogenic models proposed by Ernst Mars, right? So, but in that case, the loop is not so simple. It contains our particle inside. So in that case, it's hard to make the specific predictions on the diameter mass, since the loop function is so complicated, and it depends on many coupling constants and heavy particle masses. So it's hard. But this one is so simple, just diameter loop. So, and the lambda is like dimensional coupling. It has nothing. It just all the particles being integrated out. They just manifest as lambda. Okay. Now let's come to my conclusions. So here we propose a very simple models based on these effective couplings. Just assume diameter only talk two neutrinos in this one here. So from these operators, the diameter annihilation cross-section is determined by just simply by these operators, right? Just by n chi. So the annihilation cross-section is function of n chi and lambda. Okay. And the neutrino mass actually neutrino receive a radial mass from the contraction of these two chi's. If you contract these two, you get neutrino mass. Okay. So two unknown parameters in this one, just two unknown. One is the diameter mass, the other is lambda, can be completely fixed if we supply the rate abundance and neutrino mass. Okay. And we also provide unique complete models and to realize this one. Okay. And as I tried to emphasize before, this toy model fulfills two requirements. The first, the left number violation comes from hidden sectors, and which based down to the stellar sectors only through diameter. Okay. The second, the heavy particles associated with the scale lambdas, actually do not enter the diameter loop. So which make this model more predictive. And as an outlook, I would have point out some kind of possible signature for these models, and also some tensions. So this model actually predicts the NEV neutrino flux from the S-wave diameter annihilations, which could be detected from like supercommon conducts, snow, bone signals, etc. This kind of neutrino experiment. Okay. But if you look at my toy models, actually the phi here, the fact the lambda is GeV, actually it implies sunlight particles, right? The lambda is like 1 GeV, is much below the electroweak scales. So which implies the existence of sunlight particles. In this case, it's phi here. The phi actually can contribute to the Higgs invisible Higgs decays if the phi coupled to Higgs boson directly. If okay. Also, given the GeV phi, as I tried to mention before, the heavy neutrino is around TeV with relatively large Euclid couplings, so it could be produced at the LHC. Okay. But actually, it has some problems. Since the NEV neutrinos, when they decouple from the thermal base, they will give their entropy into neutrinos, so they will reheat the neutrino sectors. But actually, this one will be detected from the CMB measurement. Since from CMB we know that the neutrino species is the so-called NU is a relativistic species. It's around 3 point something, 3.3, right? But in this model, it gives you 4.4. So it's kind of in tension with this one. But again, keep in mind, this one is just toy model. I only include one flavor. So one can think about the better toy models, which include all the neutrino flavors, and at the same time will make the NEV neutrino kind of heavier. Since this kind of constraint from this paper, this one only applies to the particles below like 8 NeV. Okay, if your particle is like 10 NeV, then you are fine. You don't have this kind of constraint anymore. Thanks, I'll stop here.
Any questions?
I have a comment. Actually,
Yes.
the neutrino mass is proportional to dark matter mass, or over the cutoff lambda.
Yes.
So, I mean, it's not that predictive. Because lambda is free in your model.
Sorry?
Lambda is free in your model, the cutoff scale.
Yes, of course. So we need two conditions.
Yeah.
Yeah, in that sense, yes. We have two conditions, neutrino mass and the rate abundance, which just diameter and annihilation cross-section. Yes.
But if
Thanks.
you have more than one favor, then you still have this universal also cut off as a proportional constant, and it will more predictive.
Depends on how.
How your model feels.
Yeah.
So how many C or factor n you need to find the neutrino oscillation data?
Neutrino oscillation.
Data,
Yeah. Yes, at least two. I think two generations. If you do.
You mean 2 C and 2 n.
Yeah, but how to say? Actually, maybe one is not. I haven't thought about the question here. Since this one is coupled to a neutrino, yeah, probably you need at least two here to accommodate 2 delta m squared. I think at least two in the concrete model. Yes.
2 means 1 C and 1 n, or 2 C 2 n.
2 C to a 2 Dirac fermions, 2 Dirac heavy neutrinos. Thanks.
Any more question or comment? So if not,